But yeah, have a calculator out because while you could do the calculations by hand for comparing two means, it's super tedious and would has plenty of places for computation error. So we're just going to kind of rely on our calculator literacy to be able to do this. So this is very similar to when we were comparing two proportions. Um, so oftentimes we're interested in comparing one mean to another. So like maybe you think one mean is greater than or one mean is less than, or maybe you're just interested in whether they're not equal to each other. So means from two different samples. And so today we're going to be creating confidence intervals for the difference in two means, because all of these can just be rewritten as the difference in two means by subtracting 1 over, like so, and then comparing it to 0, right? So we're going to be creating a confidence interval trying to capture the true difference in two means. But that means you're going to have to check conditions again. So I will just remind us of the conditions. They're the same as they always have been. Random 10% large counts, right? Random, you need to make a statement that the data come from two independent random samples or that you're dealing with a randomized experiment. 10%, if you're sampling without replacement, you just need to make a statement that your first sample is less than 10% of your population and your second sample is less than 10% of the second population. Again, an easy way to do this is just multiply your sample size by 10 and state that it's safe to assume your populations are bigger than that, right? And then large counts for a mean. Who remembers what the large counts condition for a mean specifically is? For a proportion, it's n times p is greater than 10 and n times 1 minus p is greater than 10. For a mean, it's just based on sample size. How large does your sample have to be? 30 or greater, or if you know that the population was normal, it doesn't have to be 30 or greater, right? If both of those aren't satisfied, you graph the data. You graph the sample data, make a little box plot. In this case, you have to do it for both samples, okay? All right. And then you just make a statement that there's no strong skew or outliers in your sample, and then you just move forward. So we'll see a couple examples of this. I'm going to move pretty fast, I think, through the checking conditions. Hopefully this has become pretty rote, right? We've done it so much now, but it's just a necessary thing. What I'm really more concerned with about this, I know you can check conditions. It's just a matter of memorizing what the conditions are. But I want you to be able to interpret results, right? So making sure that you can actually run the test in your calculator, making sure that you understand what the results mean. So I'll move pretty quickly through checking conditions so that it doesn't get so tedious. And if you need to go back, I'm recording this and I will post the lecture to Canvas. All right, so let's take a look at this problem. I need to open up my calculator. All right, a college student wants to compare the cost of 1 and 2 bedroom apartments near campus. She collects the following data on monthly rent in dollars for a random sample of 10 apartments of each type. Let M1 be the true mean monthly rent of all 1 bedroom apartments near campus, and mu2, did I say M? I meant mu. Mu2 be the true mean monthly rent of all 2 bedrooms apartment near campus. Check if conditions for calculating a confidence interval mu1 minus mu2 are met. This one I actually want to do one of the conditions just to remind us how to graph, because we'll assume it's a random sample. It says it's a random sample. 10% condition, well, there's more than 100 apartments in any large city, right? So safe to assume 10% condition is satisfied. But large counts is not satisfied, right? There's only a sample size of 10 for each one. And we're not told anything about the distribution of apartment rent. So we don't know that it's normal. So we would have to graph these. And I just want to remind you how to graph these, because you would have to graph 2 box plots. So let's go ahead and put 1-bedroom apartments in list 1 in our calculator and 2-bedroom apartment cost in list 2. So I'll go stat, edit, and I'm just going to enter the apartment rent cost for 1 bedroom in list 1 and 2-bedroom in list 2. I'll leave that there so you can copy down that data. Okay. And so what we want to make, once you have that data entered, what we want to make is parallel box plots, which your calculator can do for you. I'm just going to go into y equals and clear out any graphs I have there so I don't have any nonsense graphing over my nice box plots. All right, then I'll go second stat plot. I'm going to go into plot 1 and make sure it's turned on. Choose the box plot that has outliers. And then I'm going to tell it that's from list 1. Okay. Now I'm going to go second stat plot again, and I'm going to turn plot 2 on. Again, choose the box plot that has the outliers next to it. And then I'm going to change my X list to list 2, which is just the shortcut is second 2. There we go. Quit to the main screen. And then I'll just do a zoom stat. So zoom 9. Whoa, did I screw up entering my data? Does yours look like that?
It's just like lower down.
All right, so let's see. Yeah, it doesn't look like I did. Okay, so there you go. The thing that you would want to do, so you would copy these box plots down just like this. Then you need to put an x-axis below it and label it with some scale. The scale you can use is just if you hit trace, I would just copy down on the x-axis like the 5-number summary for each. So basically you would have 10 tick marks on your x-axis. And then you would want to label your x-axis with what the data is. So this is monthly rent. And then the top one is the 1-bedroom apartments, and the bottom one is the 2-bedroom apartments. And then we would just want to state that there's no extreme skew or outliers. So I'll show you kind of what the text did. Oh, they created a dot plot. That sucks. But yeah, box plots I think are the easiest to do. So it says no outliers or strong skew.
What does strong skew?
In a box plot? Good question.
I would have looked at that and been like, oh, that's a strong skew. I don't know, just because I'm not quite sure.
No, it's a great question. So confidence interval for mu1 minus mu2, we do the same thing. We take a statistic, we add and subtract a critical value times the standard deviation of the statistic. In this case, our statistic is going to be a sample mean 1 minus a sample mean 2. And our formula for standard error will look like this. This is actually standard deviation, but again, we won't know the population standard deviations. So instead, we end up using sample standard deviations, and we refer to this as the standard error. All right, all of these are formulas that you have. These are formulas in your formula packet. But remember, when we're talking about a mean, our critical value comes from a t-distribution that's determined by the number of degrees of freedom. Now, in this case, the formula for degrees of freedom is actually more complicated when we're using two samples. The good news is you don't have to compute it. Your calculator will do it for you. All I need you to do is notate how many degrees of freedom your calculator tells you it has. If we were doing it by hand, the way to do it is just choose the smaller of n1 minus 1 or n2 minus 1. So whichever one is smaller is your degrees of freedom. But again, we're not going to worry about that. You're going to run the whole thing in your calculator, and it'll spit out some degrees of freedom that you'll just copy down. All right. The Wade Tract Preserve in Georgia is an old-growth forest of longleaf pines that has survived on a relatively undisturbed state for hundreds of years. One question of interest to foresters who study the area is how do the size of longleaf pine trees in the northern and southern halves of the forest to compare? To find out, the researchers took random samples of 30 trees from each half and measured the diameter at breast height in centimeters. Here, that's a measure, okay. The DBH. Here are summary statistics and comparative box plots of the data. All right, great. All right, so they're just going through again, checking conditions. The shape of the distribution of the northern sample appears to be slightly skewed right. So again, there's another example of a right skewed box plot. And the south is slightly skewed left. Neither of those is a particularly strong skew. And there are no outliers present in either sample. Center, it appears that the trees in the southern half have larger diameters on average. We can see that the medium is larger than at the northern. And there seems to be more variability in the northern longleaf pines. It's just a wider distribution, right? All right, so what I want to do is construct and interpret a 90% confidence interval for the difference in the mean DBH of longleaf pines in northern and southern halves of the Wade Tract Preserve. So what we'll do is mu n minus mu s. So true mean difference in DBH. And that's, once again, north minus south. All right. Let's go ahead and assume all conditions are met. It's a random sample. There are more than 300 trees in the north and 300 trees in the south. So 10% is satisfied. And then we already have large count satisfied because we took a sample of 30 for each one, okay? I'm not going to take the time to write it out. You have to write it out on an exam. You'll lose like half the credit for a free response problem if you don't check conditions. But I'm going to walk us through how we're going to do this in our calculator, so grab your calculator. All right, here we are given summary statistics. We're not given raw data. So we're going to go stat. We're going to roll over to tests. This is 2 samples, so we're going to be looking at 2 samples. It's not a test, it's an interval. And it's for a mean, so it's not going to say mean. It's just going to say 2 sample t interval. So it's this 10th option, or option 0. We're going to choose that. We're going to input stats, not data. All right, so our first mean, go back here. We're doing the north first, so it's 23.70, and the standard deviation is 17.5. My first mean is 23.70 standard, come on, 23.7, 17.5. Standard sample size rather was 30. All right, for the south, my mean is 34.53. My standard deviation is 14.26. My sample size is 30. The confidence level that they ask for is 0.9. Pooled is always going to be no. Just leave it as no. And then we'll go ahead and calculate. All right, the things you want to write down are the first 2 lines, your actual confidence interval itself. So it's from negative 17.72 to negative 3.936. And your degrees of freedom. So DF is 55.7. I'm just going to go 3 decimal places, 728. All right. That's it. So now we're ready to conclude. The script is the same as it always has been for a confidence interval, right? So you say, we are, in this case, 90% confident, that, and then you state your parameter, which is the true difference in dBH, and I'll do north minus south, falls within the interval negative 17.72. What are the units here? Oh, centimeters to negative 3.936 centimeters. So sort of what conclusion can we draw about the heights of the northern versus southern pines in this case? Yeah, southern is tall. We're confident that on average southern is taller. And the reason we can draw that conclusion based on this confidence interval is what? They're all negative. If the interval contains 0, could we draw that conclusion that one is taller than the other? No.
Will they ever ask us to like interpret the degrees of freedom?
No. Absolutely not, which is why I don't cover it too much. You just need it as a means of calculation at this point. But if you take a higher level statistics class, they'll talk about what degrees of freedom are. It's just it's beyond the scope of this class. All right, we're good. Hey, yeah, let's practice running the confidence interval from the apartment data. So that should still be in your calculator, right? So let's do the same thing. This was 1 bedroom minus 2 bedroom apartments, right? Like list 1 was 1 bedroom, list 2 was 2 bedroom. So if you go back and stat tests and then choose the 2 sample t interval, we're now going to run it off data. And then it should default to list 1 and list 2. We put our 1 bedroom rent in list 1. We put our 2 bedroom rent in list 2. Keep your frequencies at 1. And then again, pooled is no. That's fine. We can leave our confidence level at 90%. Go ahead and calculate. You can see your confidence interval. So the true mean difference in monthly rent, 1 bedroom minus 2 bedroom, is somewhere between negative $144.80, negative $11.20. What can we say about the cost of 1 bedroom versus 2 bedroom apartments? Yeah, the true mean cost of 2 bedroom apartments is more expensive than 1 bedroom apartments because the interval is fully negative and we did 1 bedroom minus 2 bedroom. Make sense? All right. This AP exam tip just says, don't do this by hand, use your calculator, and just make sure that you always do no pooling in your calculator and that you also list the degrees of freedom when you write out your answer. All right, but there's a little wrinkle in this, in that sometimes you're given 2 sets of data, but it's not a 2-sample test or a 2-sample interval. And the reason for that is that it's paired data. So it's really 1 set of data that's kind of disguised, almost looks like 2 set, but when you read the context of the problem, it's actually going to be 1 set of data. So I want to make sure that you understand the difference between what we just did and paired data. So here's an example of paired data. So a researcher studied a random sample of identical twins who had been separated and adopted at birth. In each case, one twin, twin A, was adopted by a high-income family, and the other twin, twin B, by a low-income family. Both twins were given IQ tests as adults. And here are the results. So we did this for 12 sets of twins. Now, obviously, a sample size of 12 doesn't satisfy the large counts condition, so we graph the data. In the sample, we say there's no significant skew or outliers. Now, what this researcher probably wants to know is there a significant difference in IQ between high-income twins and low-income twins, right?
There's a lot of factors in this they're not considering.
Totally. And this might look like, okay, well, what we want to do is a 2-sample t interval for mu1 minus mu2. But the problem is you are comparing twin to twin. You're not comparing sample to sample, right? You're comparing each individual twin with the other twin. So that's different than taking a random sample from group 1 and a random sample from group 2 and then comparing them, right? In fact, in this case, each individual datum is paired with another datum. So paired data result from recording 2 values of the same quantitative variable for each individual or for each pair of similar individuals. So really what we want to be looking at is just the difference in A minus B for each set of twins. So all we want to look at is this single set of data, which is twin A IQ minus twin B IQ. And so really this is only a one sample situation where the sample is just the difference in each twin's IQ. And so then if I wanted to run a confidence interval for the difference in twin A minus twin B IQ scores, I would enter that data into my calculator, and I would just run a one sample t interval on that set of data. Okay, so my point is it's really important to make sure you understand the context because the proper method of analysis depends on how the data are produced. If it's a random sample from one population and a random sample from another population, you're going to use a two sample t interval or a two sample t test or z interval or z test, depending on if it's a mean or a proportion. But if the data, if it's just two sets of data and you just immediately start doing a two samples test and don't realize that it's paired data, then you're doing the analysis completely wrong, right? So to analyze paired data, you first look at the difference for each pair. That'll give you a single set of data, and then you run a one sample interval or test. So let's look at just another one with paired data. So does music help or hinder performance in math? Student researchers Abigail, Carolyn, and Leah designed an experiment using 30 student volunteers to find out. Each subject completed a 50-question single-digit arithmetic test with and without music playing, and for each subject, the order of the music and no music treatments was randomly assigned, and the time to complete the test in seconds was recorded for each treatment. Here are the data along with the difference in time for each subject. So in this case, each student is actually paired with themselves. So you are taking the test with music, and then you're also taking the test without music, and you're comparing your own scores, your own times, right? And so really the only data that we would focus on in this case is specifically the difference with music and without, right? This last row. So music minus without music here. And then we would run the t-test. So let's just do that. Let's practice it with this data. Go ahead and enter that last row of data. So there are 30 values into list one. Oh, that's pretty small. So I'll do them and you can follow along. So let's go stat edit. We're just going to go into list one. All right, so we have 13, 13, 6, 8, 5, negative 6, negative 13, 0, negative 5, negative 7, 9, 7, 8. Nope, I'm sorry. That one was supposed to be negative 8. 9, negative 2. All right, 5, 20, 12, 7, negative 2, negative 2, -2, -2, 4, -4, 11, 5, 4, and -3. And 2 more, 4 and 2. Okay. All right, so what we've entered there is the 30 difference in times to complete the arithmetic test, and that's music minus without music. And so if we wanted to analyze that data, we could create a confidence interval, and I would go stat tests. And since it's for a mean, I would go to t interval. I'm going to go from data list 1. Let's just do confident. Let's do, I don't know, let's do a 99% confidence level. Calculate. All right, so the true mean difference in arithmetic test times when listening to music, subtracting when listening to no music, is between -0.9692 seconds and 6.5692 seconds. Do we have any evidence that listening to music or not listening to music causes students to do better at arithmetic? Why don't we have evidence? 0 is in the interval, so there is, basically we're saying there's a chance that there is no difference, right? Good. All right. All right, I'm going to give you a couple minutes. Go ahead and read through this problem. This is from the 2009 AP Stats free response section. What I want you to do is construct a 95% confidence interval given this data. I will say, just go ahead and assume conditions are met, even though in reality I would need you to check all conditions on the page. But I want you to, in your calculator, create the confidence interval and then be able to answer part B for me. So I'll give you a couple minutes to do that and then we'll go over it. It's exactly what I get. So I did mu north minus mu south. You could have done mu south minus mu north. You would get a slightly different interval, but that interval should still have one very important characteristic that it's going to allow us to answer the second question. Does the confidence interval in part A support the council members' belief that the two fire stations have different mean response times? Yay or nay? Nay. And the reasoning is? The interval contains 0, so 0 is a plausible mean difference in response times, meaning there would be plausibly no difference in response times with 95% confidence. Does that make sense to everybody? So not too bad. Just remember, again, I'm setting a bad example because we have a short class today, but you have to check conditions on paper, right? What are the conditions? What's large counts for a mean? Excellent. Good work, guys.